be talking about benchmarking those models against other platforms out there, for example, the GPU, the CPU, so on and so forth. We have our own benchmarking framework with a composable benchmarking methodology called MLAgility. Everything is completely open source, and in this section, we'll be talking about MLAgility. So let's begin with an overview of the agenda of the topics we'll be talking about right now. Let's start with the devices and runtimes currently available in the MLAgility benchmark. We'll go into the benchit CLI, which is the command line interface for the MLAgility benchmark, which allows you to benchmark whatever model you may have against whatever hardware and also whatever runtime you may be interested in. After that, we'll be talking about how you can write scripts with MLAgility such that the benchmark can be able to extract and also run those models. Then we'll be looking into report generation and also visualization. If you remember the Hugging Face public page we showed earlier, that's something you can generate on your own. It's completely open source, so you can host your own website if you'd like in the same format, or you can even do it in your local host. It's just a much easier way to visualize these benchmarks. I'd recommend using that, and we'll go through that shortly as well. And finally, we'll talk about the current limitations within the framework. Like we mentioned earlier, this is all under active development. There's a lot of work which we do have in the pipeline, and we'll talk about where we'd like to be in the near future and how the setup would look like as well. So without further ado, I guess let's begin. Go to the next slide. So let's talk about the devices and also the runtimes available in the MLAgility benchmark as things stand right now. We have 3 hardware offerings. That's the NVIDIA GPU system and the Intel x86 CPU system. And of course, how can you miss Grok, right? And alongside those hardware platforms, we have associated runtimes to go along with them. For the GPU, we have TensorRT. Bearing in mind, MLAgility, it's focused on inference workloads. Grok is focused on inference workloads, and we are very interested in benchmarking inference workloads. TensorRT is an optimized runtime for NVIDIA GPUs. And it's something which, once you set up a Docker image, you can run models with TensorRT on V100s, A100s, H100s. It's all backwards compatible. Now, going on from the NVIDIA system to the Intel system, we have quite a few runtimes. We've got Onyx Runtime, and that's using Onyx Runtime GPU. You can pip install that. You do have to specify the execution provider. That'll be Onyx Runtime CPU. We also have other runtimes as well, for example, PyTorch Eager and PyTorch Compiled. I'll be talking about comparing runtimes later on, but right now what we're doing is we're comparing device with a default runtime against each other. And of course, for the Grok system, we've got Grok Flow. As the runtime, Aviv will be talking a bit more about the runtime as well. Grok Flow is kind of the package which allows you to compile and also run all these models. All right, and let's go on to the next slide now that we've talked about what we have. We've got this command line tool, which allows you to benchmark all these models. All you have to do is just specify them within a file. In the next slide, we'll be talking about how you can set up that file to be able to run this MLAgility CLI tool. But for now, let's just look into the commands which you need to run the benchmark. All you have to do is specify the benchit command. That's on the second paragraph on the left-hand side, right in front of you. Benchit, specify a path for your model. So for example, right here, we're using BERT. And all you have to do is specify the device. So Grok, NVIDIA, or the CPU. And once you run that, you'll get something in your terminal looking something like the above on the top right-hand side or the bottom right-hand side, depending on the device which you select. So if you're running it on the CPU, it tells you the latency and the throughput, and also tells you that you've benchmarked it on, let's say, an Intel Xeon CPU with whatever frequency, with whatever version of Onyx Runtime. We try and be as explicit as possible with our runtimes, so it's much easier to compare and contrast against other vendors and other runtimes as well. And on the bottom here is just another example of using another device, for example, the NVIDIA offering. Again, it tells you the latency, the throughput, and also what device you're running on. So in this case, it's the NVIDIA A100 and it's 40 gigs. Gives you the outputs and it tells you, woohoo, it's done. And as before, everything is saved in a .cache directory. Similar to Grokflow, we save it in your user .cache directory, and all of the files will be available over there. So if you were to want to benchmark, or if you were to want to, for example, compile all of your benchmark results, it's going to be saved in your .cache directory. All right, so that's a very high-level introduction to the tool. Now, let's talk about how you can write scripts to be able to interface with the tool. So if you look at the right-hand side, that's an example of a script which works out of the box with MLAgility. It's very similar to the setup which we had for Grokflow earlier, but you do have to specify a few more parameters. So for example, all you have to do is import MLAgility.parser, and that allows you to kind of argparse these arguments you want into your script. You import whatever model you may want. So you need the transformers library to get, what model is this? But import torch, specify your hyperparameters, create your model, get your inputs in a dictionary format, very similar to Grokflow, and you call it. So we do have almost a format to write these scripts, but it's extremely simple. And if you've written something within Grokflow, it's so easy to get into MLAgility. A lot of the issues you may have would be within the Grokflow setup, getting things to run. And we've talked about how you can debug things. And of course, feel free to contact us if you have any issues. But once you get something to run, you can just almost immediately put this into MLAgility, and you can benchmark this against all the other devices and runtimes which you may be interested in. So yeah, that's how you can create a script with a model you may be interested in. Let's talk about how you can benchmark multiple models. So in the above slide, we're just looking at a single model. And for a benchmark, sometimes you're looking at thousands, hundreds, maybe even millions of models, and we'd want to be able to benchmark them with just a single command. And we have this functionality within MLAgility. All you have to do is just specify benchit, and you use the asterisk to say that you're benchmarking all of the scripts within a single repository. And you can also use another asterisk in front of all your Python files saying that you want to benchmark all of the directories within a current directory. All right. So on the above, what you're doing is you're benchmarking a single model. And on the bottom line, what you're doing is you're benchmarking all the models in all the models in all the directories in your current directory. And everything, as we mentioned earlier, is going to be saved in your .cache file. And you can extract all the information from that. The way you extract all that information is you use this command called benchit report. Right now, this is under active development, and we're still working on this because we'd like to be able to extract more information from your cache folder. So this may give you unexpected results, but rest assured, we're working on this. And effectively, that's all we have MLAgility. So before going on to sorry.
Quick question. The NVIDIA, what NVIDIA hardware would we be using if we're in this?
You could use any GPU you'd be interested in. For example, right now we're using this on an A100 on the GCP cloud system, but you can also do this with the H100, the V100, the T4, so on and so forth.
So you basically run a separate instance of it wherever.
Yeah, I was hoping to show a live demo of this, but
okay,
there aren't
thank
any
you.
A100s available right now in GCP. But all you do is you just I'll go through this later on. You clone the repo, and all you do is you just specify NVIDIA, and it should be handled for you. I've tested this on the V100, the H100, and the A100, and they both seem to be working okay. but other devices and maybe other cloud platforms that may be a bit, not out the box. Does that answer your question, Bill?
Yeah, I think so.
All right. I guess now that we've gone through that, maybe we can go through a live demo of MLAgility and go through some code. Let's go into the public MLAgility repository. One second, the zoom bar is messing with my Chrome tabs. Let me just do that quickly. And then full screen again. So this is the public MLAgility repository. To navigate to this, all you have to go is to go to our public grok repo and find MLAgility, and that's going to be right here. I've made a few changes this morning, so what I'd like you to do for now, just in the near future, is to use the ANL workshop branch if you were to run this right now, and just clone this. There are some installation instructions, so let's just go on that to get all of us up and running. So very similar to before, you have to use Miniconda. That's our package management system. We haven't tested against other package management systems, but you're more than welcome to try Python venv, for example. It's just that we haven't tested against it. I'm not going to go through these steps because we've already gone through them, and it takes a bit of time. So maybe I should skip this, or maybe not. Actually, let me just do that just in case and see how that works. Here is number 3. Here is one of the nodes on the replica rack, and let's just go through the installation one by one. First, let's clone the repository. And then we need to create a virtual environment. So let's go convert create .n MLA Python equals to 3.10, and that's going to be the same Python you use for your Grokflow environment. I suppose that's something we should add to the documentation. So I'll take the lead on that. And after we do that, we move into MLAgility and just pip install. Now, an issue you may have with a pip install is they may want you, there may be an issue with doing a global install, for example. So you may have to specify the -- user flag on the pip install so that you save everything in your .local file. Okay, so we've got the MLA environment set up, MLAgility, and let's do the pip install. I'd avoid spending too much time on this because it's just pip installing something. So let's go back to this other node within the same rack where I've actually even already activated the environment. All right, so I've activated the MLAgility environment, and I'm not in the correct repository. So let me go into MLAgility. And there we have all of our files. Let's try and run a single benchmark. So what models do we have? Maybe let's look at the examples first and go into CLI, scripts, maybe hello world. So over here we have just a linear model, very similar to the first example we did with Grokflow. And it's using the same format as we did with Grokflow, and also the format which is required for MLAgility to work. So let's try and run this with the benchit command. Benchit, I'm going to go find that path. mode. So all you have to do is specify benchit, pass in your input Python file, and then also specify the device that you want. If you don't specify the device you want, it defaults to the CPU. But let's just try running it on the CPU for now. So as you can see, it's building in your .cache file. As Murali asked before, I'll have a look into how you can save this into a different directory. It's definitely possible. I'm not sure if it's
Atish mentioned pointed to a link on the documentation, and yeah, we can. There's a way to do that. Yeah. Thanks.
All right. And while we're talking about that, it's already complete. So we've benchmarked this linear layer on our current CPU. So I can kind of ls CPU this, and we can see the CPU we have, EMD Epic x86. That's exactly what we've benchmarked on. And you get the latency and also the throughput and also a snippet of the output. Now, that was the CPU. Let's try this on the GPU. Sorry, let's try this on the Grok system. We don't have a GPU instance up right now. And there you go. It's been successfully benchmarked on the Grok chip using GrokFlow v2.2.1. And in fact, the mean latency is too small to be noted within 3 significant figures with milliseconds as a unit. But you have the throughput, and you also have a snippet of the outputs. And like I mentioned before, everything is in your cache folder. So now we have an MLAgility cache. And I actually did a sweep very recently. And this is where we got the results to populate the public Hugging Face repo. So let's just look at how one of these looks like. What's a good model? Maybe GPT-2. And let's look at the MLA build. Let's look at the MLAgility stats.yaml file. And this gives us all of the information provided by MLAgility, gives you a number of parameters within the model. In the future, we're planning on using this public library called Onyx Op Counter. In addition to having the parameter count, we're looking at adding the flop count as well. So we can look at the flops per second as another metric for measurement and comparing all these different hardware platforms. But over here, that's the main takeaway from MLAgility, the performance. We're running this on the Grok chip. That's the model we're running on with the hash attached to it. The latency with the units attached, the runtime, of course, Grok runtime, and also our throughput and the units for throughput, which is inferences or iterations per second.
So there's a question on the chat window from Richard. It says, like, on the CPU, how do you control the number of threads?
Sorry, how do I find the
It's in the Q&A.
It's in, yeah, Q&A below. If you can't find it, let me just repeat what Murali said. Richard Loft is asking, on the CPU, how do you control the number of threads?
So I think this depends on the runtime that you're using. Within some runtimes, you can specify the number of threads via parameter. But I think we're using Onyx runtime right now. Onyx runtime, and I believe it uses a single thread. But of course, this is something, because it's so composable, you can kind of specify that yourself and add your own runtimes as well. Does that answer that question?
Richard, if you want to follow up, let me see.
I'll just continue moving on.
Yeah.
Yeah, I mean, I could follow up and just say that, typically you'd like to sort of max out the number of threads, or understand not just the single threaded performance, but what is sort of intra tensor parallelism gives you, or something like that, for the inference performance.
Yeah. No,
So yeah, it's like saying you want to make sure you're doing a fair comparison. But I don't completely understand. Well, I'm not familiar with like the Onyx runtime, so I wouldn't. I guess I don't understand. How you would actually do that. It sort of comes down to like set num threads equal, right, to some value or something. But I don't know where you would put that in.
I'm just looking
in
at,
in PyTorch you have a kind of specification that you can do to set that value.
yeah, I think in PyTorch it's like an OpenMP type setup, and you just specify the number of threads to the CPU.
Yeah, there's like a torch dot set num threads, and then a value, but I don't know how you do that. I suppose that's something you can find out by grepping around in like you're searching around in the Onyx runtime. Oh, there you are, right there. What is that?
Yeah, it does look like there's an API call to do that, but also like you mentioned, well, something to add on to what you've already mentioned. Sometimes even if you max out the number of threads, you get kind of diminishing gains, and sometimes you reduce in performance when you add more threads because there's kind of too much orchestration going on.
Exactly. Yeah. Sometimes you get a kind of parabola, shaped curve. And so you'd want to sort of probably tune that or run a few values to sort it out.
Yeah.
I think the answer is that there seems to be something in Onyx that you can that you can set and control. So I'm satisfied with that answer, I guess. I don't want to delay you anymore. Yeah, this is an example from the torch for doing this, and shows the diminishing returns, right? At some point on the right over there, you see the time starts going up again, right? So there's some, typical sort of thing there going on with the performance.
Yeah,
All right.
yeah, exactly. And I think we're running on a single thread right now, but again, because everything is, again, MLAgility is open source and it's really composable, we can do a similar analysis for this even on the CPU, comparing the same application on multiple threads, for example. That's something we could do on the runtime side of things.
Okay. Well, thank you very much for taking the time to sort of chat about that.
No, you're very welcome.
Just quickly, I think from my understanding, Onyx runtime, it will run with multiple threads by default. So I think it will see the number of threads you have available, and then it has some extra settings to allow you a little bit more granularity with if you're specifying it for inter and intra-op, but it should run with multiple threads by default.
Thank you, Philip. Yeah, that was something I wasn't aware of, so thanks for clarifying. Yeah. I guess we can kind of go on and step through the presentation, the rest of the presentation. Once you have, for example, benchmarked a single file with the same command we talked about before, you can benchmark an entire repository. So for example, if you wanted to benchmark all the models within your scripts repository, all you do is you just write an asterisk right there. And what you're doing is you're benchmarking all the Python files. I'm not going to do this right now because it's going to take a bit of time, but the output is going to be very similar to what you see over here. You're going to have all the models saved in your .cache folder. And maybe let's go back to the presentation, because what is the next thing should be looking into. Okay, the report generation, that's something we're still actively working on, because we'd like to understand a bit more about where compiles fail and so on. So we don't have this functionality available for you right now. But you can, for example, what we've done is I just wrote a script which greps the latency, just scraping through all of these directories. And once you get that CSV file, we have, for example, within MLAgility, let me just try and find that directory. We have the trackers directory, and this is a Streamlit app. What you do is you put in your CSV, which is all the data from your model, from your benchmarks, and you run the Streamlit app, and you'll get something very, very similar to this, or identical to this in your local host. So I kind of just speed run the last few sections, but in conclusion, we're still working on the report generation side of things and converting everything to a CSV and getting more data about when compiles fail. But once you do get the CSV, we have this public, sorry, under trackers, we have the Streamlit app, which you can run, which generates this page over here. All right, so I guess that concludes the coding section of the presentation. I do want to talk a bit about the limitations and future work. We kind of touched a bit about the limitations just now in terms of, let's say, multi-threading on the CPU, and then thanks, Philip, for the clarification. But let's go a bit more in depth about this as well. So one of the key points to note about the Grok results is we don't take runtime into account right now. All the numbers you see quoted on the Hugging Face page, that's cycle count divided by the clock frequency, added by also estimated PCIe latency. So it's a theoretical analysis on the runtime side. We don't include the runtime, it's just the IO for the PCIe, plus however long it takes to run on chip. That's one of the biggest asterisks we have right now for MLAgility, but it's something we're working on. We're working on including runtime performance as well. And as the runtime becomes more and more mature, we'll get better and better results on that side. Other limitations are we only benchmark on batch 1. That's really where Grok shines. We work on real-time batch 1 inference, but of course not all workloads are batch 1. And that's something we want to add to MLAgility as well. What else do we have? Yeah, and on the bottom right side, we have a limited number of models, devices, vendors, and also runtimes. We like to be able to benchmark against more models, for example. On the Hugging Face page, we are 168. And our internal page, we have around 1,000, but still, we'd like to have significantly more than that, and benchmark all those models against different hardware vendors, different runtimes, and see, how everyone stacks up against each other. Other things we're looking at working in, other things we're looking at working on are, for example, including power measurements, including accuracy measurements, because different hardware vendors, for example, have different data types, and that may result in different outputs for the same model. We're interested in including operator microbenchmarks, so just looking at a single operation, for example, a matmul, and seeing how that scales from maybe going from single chip to multi-chip, a multi-rack system, for example. And as I mentioned before, increasing more devices and more runtimes. And that concludes the MLAgility section of the presentation. And in conclusion, MLAgility is a fully open source benchmarking tool. Just have a look at the repository online and play around with it as much as you like. And we use it to benchmark hardware and also runtimes.